Thank you. So, wonderful talk this morning. We're going to continue. It's my great pleasure to introduce Philando Paganini, all the way from Uruguay. So, Philando graduated from Caltech in 1996. And I think almost everyone here has either read his book, a paper, or both. So for me, the first time I know Philando's name was through the book, A Course in Robust Control Theory, a Convex Approach, which is a great introduction, took me into the control theory, and also helped me and my friends to pass our qualification exam, the CDS, back 2007. So thank you. The book's still in my office, and all my students have to read the book before they join my group. Yeah, quite nice there, so can confirm. And so when I started learning the utility of maximization and primordial dual algorithm, then again, I found a lot of inspiring papers written by Philando and also Steven. So Steven and Philando have been collaborating for many years, from internet congestion control to the power system dynamics control. So their joint paper is not just providing theory or providing algorithm, which of course are the ones our optimization and control theory, but also greatly improve the performance of the real-world systems, either is internet or the power system, which we can actually say they are the two largest networks that our society have ever built. And lastly, I would like to thank Philando for taking the long flight all the way through Uruguay to here to join the event. Without further ado, let's welcome. Thank you.
So thanks. Is this functional? Yeah. Thanks, Lena, for the great introduction. I want to thank the organizers for having me inviting me to this great event. It's always a treat to be back at Caltech and meet a lot of friends, but also it's an honor in this case to get to give a long talk in tribute to Steven, who has had a great influence in our careers. So my talk will have two parts, and I guess I'm also turning 60 this year, so I guess I can indulge in a little retrospective thinking. In fact, I just found out that Steven and I were both born less than a week of a difference. So you'll indulge me, you'll forgive. And then the second part of the talk has to do with the more recent technical problem, but so the first part will be more like looking back, but you'll see that there's a lot of cross-connection between both parts. So let me just jump first into the retrospective. And I was thinking about optimization and control, the two main themes, and also networks. And I thought, okay, the first serious interaction between optimization and control was probably optimal control from the 1960s, when Steven was being born, and myself too, but of course we didn't have any say on that. So then the main way it was presented in those days was we want to optimize trajectories, finding inputs that takes us to places in an optimal way. But of course, feedback started popping up in the solutions, which gave a very rich theory, which in other incarnations continues to this day, dynamic programming, reinforcement learning, and so forth. So those are the origin, I think, of the interaction between optimization and control. And it's still, open loop optimization is still very, very influential in practice in MPC and things like that. Okay, so let me just jump forward and go to the 80s and 90s, which is when I got into control theory in the early 90s, a student of John. And so we were looking at this kind of picture where feedback, we were after feedback, that was the main thing we were trying to design. And optimization was the way we measured performance or perhaps robustness of these systems. We looked at the closed loop given by a certain feedback controller. It has to be stabilizing. And then we asked the question, what's the one that minimizes some operator norm, input-output norm? And that's when I learned at least the importance of convexity. So I learned about convexity at that time. You can solve problems that are convex in some form. And, but of course, the problems we could solve at the time were centralized control, single decision maker, single objective, global information. So what happened when you go to decentralized control? People were doing decentralized control for a very, very long time in industrial processes, in the power grid itself. Lots of systems were being built based on local loops instead of one global loop. And this was my view around 2000, and I bring up this date because that's the day I met Steven. In 2000, there was a workshop here at Caltech, and these pictures are basically from the talk I gave in that workshop on decentralized control. So we were trying to map this problem into a feedback problem with some block diagonal structure. We knew that already broke the convexity we were after. And so the question is, what could we do to save convexity or in some specific scenarios? I was looking at some results with symmetry and localized information. But I guess I thought appropriate to bring it up because that's the day we met. Of course, a lot has happened since then in this picture. There's all this SLS stuff that's been going on here at Caltech. I won't talk about that because it's not my thing. I haven't done anything of that. But I was already looking at, in that workshop, at this problem of internet as an example of decentralized control. So in the internet, you had these sources of traffic reacting in feedback to congestion, and they're only using decentralized information. So perhaps this could be a good example to work on. But of course, once you look at it, it looked daunting because it's a huge system. Congestion is coupled, so who your actual neighbors are really is the people who share the path with you, but they're not necessarily people you know. The network changes constantly. So mapping this into the previous slide seems a difficult thing. And the previous slide was hard in itself, right? So it looked like a difficult problem to tackle. And that's when I met Stephen in this event, and he basically, I don't forget what his talk was about, but I guess I learned that there's an optimization-based approach to internet congestion control. And talking to him, he said, you should go read Kelly's paper. So I went ahead and I got the famous paper by Kelly on network utility maximization, who brought the idea that to think about these problems, we should use economic language, microeconomic language. We should think of the capacity constraints as resource constraints, and we should think that these are greedy sources trying to get as much as they can of their capacity. They have a utility function, and a natural objective from a planner's perspective would be to optimize the social welfare cost subject to the capacity constraints. So an optimization problem, a convex optimization problem. And once you frame it like this, you could use a lot of things from microeconomic theory, like adding a price for each resource, accumulating prices over a path, and then getting perhaps those notions to be able to design a system that emulated this resource allocation problem. Once I learned this, one of the first things I did is I went down and wrote this block diagram. This is because in my mind, you had to write a block diagram to understand stuff, right? And so it has a nice structure. You have this R, which is this routing matrix that tells you which links connect with which sources. And it has two blocks, two pieces of decentralized blocks in it. What you do at the link level, which was called AQM at the time, and what you do at the source level. And I guess what Kelly was promoting at the time was this idea where what you do at the link level is just a model of a barrier function. The price, you had to generate a price at the link as a barrier function as you approach capacity, an approximation to this hard constraint. And then you should have sources adapt slowly to this congestion price. Okay, this was Kelly's way. And then I learned what Stephen's way was for the same problem, which was let's use Lagrangians and duality to understand the same problem. So now let's make the prices the Lagrange multipliers, and let's write down a dynamics. Already Srikanth says this, that the dynamics of the Lagrange multiplier looks like a fluid queue. So perhaps we could just piggyback on that and get an implicit way of defining prices and then propagating them in the internet. And then on the source side, you only needed to do just a demand curve, basically, rate as a function of price. Well, that's the main idea. Of course, Stephen had already proved in his seminal paper that this thing converged to the optimal solution of the resource allocation problem. But there was much more things to do. First of all, to include delays in this picture, and also to try and understand what actual TCP was doing in practice, and why, for example, some oscillations could be explained if you put in the delays in the problem. And then after that, in a very fertile collaboration with Stephen and with John, we came up with this scalable stability idea, which is utility functions that automatically give you stability across all operating points, which was like this local stability, which was a very difficult thing to imagine. And I guess this was very, very successful. I was at UCLA at the time, by the way, so we would meet often. Okay, so what happened afterwards? Well, I went back to Uruguay in the mid-2000s, and Stephen, of course, went into this transition to practice. And I must say, people have said this before, but it's very rare to find somebody who can do this theory and who really cares about the applications. There's plenty of people who will put an application up there just as an excuse to justify their theory. And when you're into it, you can tell from a mile when it's fake. And in Stephen's case, it's for real. And he went all the way to designing the protocols, as I guess Harvey already told us about, testing it, and eventually making a company out of it. And other people will probably speak about that side. So a very successful program. So I guess you could imagine after this, you could just sit back and enjoy. But then Stephen moves into another area, so complete new area. And I guess this is early 2010s, or I forget exactly the date. And I was in Uruguay, and I spent the last few years doing all sorts of networking, beyond congestion control, routing, and stuff. But that was kind of running its cycle. And in Uruguay, it was going through an energy transition. There was a lot of renewable energy coming in. So it was a good time to say, okay, I'm gonna look into this area. And when I started looking, I realized, okay, Stephen has already started it and almost finished it. But I guess when so yeah, you look at this problem of optimal power flow, and which was a very hard problem that came from a long time, and immediately had these seminal papers with Stephen, with Javad, who must be somewhere here, and on transmission networks, and then another models for distribution grids. And so this is just static optimization, but it's very useful results. And then there was some work on dynamic frequency regulation, which also that looks more closer to the internet framework with optimization. Okay, so I thought, okay, maybe it's something I can work on. I was late to the game, as I just told you, so there's not so much theory I got to do. But I did have a good relationship with the people in the Uruguayan utility companies. And together with them, over the last few years, we've been developing a toolbox, which actually starts from this, basically this paper, and adds more stuff to it. Stuff that is non-convex too. When you get into real engineering, you have to be less of a Puritan. But then this is a prototype that actually computes things at a reasonable scale. And these guys are really very enthused with it. And they've actually been using it for planning decisions on buying a battery for the grid. And actually this January, they were actually running a piece of the grid using this kind of stuff. So I guess in this case, it was me who got to get a little bit of the technology transition here. And then, of course, I did do some work later on frequency regulation with Enrique Majada, who I guess is not here. And so I also got a chance to do something in that area. Okay, so this tells you how the big influence that Stephen has had in pretty much everything I've done in the last 20 years. But there's one more. What if you go now into EV charging, which is the topic of my talk? We all know that EVs are coming into the network. We could argue about how fast, but they're coming. And you need an infrastructure to charge them, which is greatly expanded from the infrastructure you have now, because home charging is one of the options, of course, but you also could use public facilities. So people have been looking at all sorts of problems in this regard. There's a lot of people doing EVs as smart loads. I won't talk about that. But then Stephen came along in his group and decided to, okay, let's do this again. Let's do something close to practice. And I guess George was strongly involved. And we never met before, but this is the time to meet in making this happen, creating a parking lot at Caltech, where you could study problems of scheduling of EV charging. And then, of course, this also got transitioned to another company. So again, you see the pattern here. So.
The pattern is both are George. You do the when you left, and then you do this.
Yeah. So, yeah, this is. I guess our meeting was long overdue. But anyway, let me just finish this intro part, the tribute part. We've been doing some work on EV charging in the last few years from more of a queuing theory perspective. My collaborator, Andres Ferragut, is a queuing theorist by training. And there's a lot of nice queuing problems that come into this setup of the garage, because the service model is different. I'll tell you about that in a second. And there's deadlines and stuff. So there's interesting queuing problems to look at there, and we did this I guess, in the last few years. But, okay, so let me just move on to now what the new stuff is. It has to do with the dynamic set optimization in spatially distributed EV charging. So what's spatially distributed? It means that you have a bunch of these parking lots spread out in the city. You have all these vehicles that are around and they need to charge. And so you would have, basically, there's a distributed demand for charge. People would like to charge wherever they are. And there's a distributed supply of charge, which is these stations, but of course they don't necessarily match. So that's basically the challenge is what do you do to cover the demand spatially. And there's a static problem you could think of, which is called facility location problem, which is, okay, if you didn't know anything about this, where will you put these parking lots, how many, and so forth, right? And people have looked at that in various OR literature, and we looked at it a little bit as well. But the problem I want to talk to you today is not that. It's the problem, assume the infrastructure is there, and the question is, what's the right way to handle the dynamic assignment of vehicles to stations? That's the problem I'm looking at. Turns out that this problem has a lot of priors which are connected to it, and I've written 3 there. Optimal transport, which is a problem, load balancing, and selfish routing. So what I'll do is I'll spend 1 slide on each one of these bullets, A, B, C, and then I'll get to the formulation. And I apologize for the long preamble, but you get into these areas and you find that all stuff has been done, and then you have to narrow down exactly what is it that you are contributing. So let's look at optimal transport. And this is really old, right? Optimal transport goes back to Monge in the 18th century. He was thinking, what's the optimal way to transport dirt from one location to another? And it's a nice mathematical problem. And then Kantorovich came along 100 years ago or so to do a convex relaxation for this problem. So you can imagine how old convex relaxations are. And basically, I'm really writing here a discretized form, because otherwise the mathematics gets hairy. But basically, think of points in the plane, which are the places where the demand for charge arises. So I is one of these points. So they discretize, think of I as city corners. I'm at that city corner and I want to get charge. I notify some system I want charge. And there's eta I vehicles seeking charge from each one of these locations. And then the stations have this capacity Cj. And the optimal transfer problem is to see how do we match demand to supply, minimizing the cost of transporting people from I to J. This is the aggregate cost. And let's assume that supply matches demand for now. Let's not get into that. So the formulation that basically the Kantorovich formulation for this problem written in discretized form is just a linear program where you minimize the cost. So let's call this variable psi ij the amount of traffic that goes from I to J. And then you minimize the overall cost subject to meeting the demand constraint, meeting the supply constraint, and non-negative quantities. So that's look like this is a simple problem. It has a nice LP solution. But of course, this is not the problem we want. This is a batch assignment. This would say all the vehicles are there. We know where everybody is, and then we basically map everybody to a station. What we want is something more continuous. People are arriving, requesting charge, and seeking service. Okay, so what can we do with that? And so this takes me to this other problem, which is more from the computer networking side, which is load balancing has already been mentioned here in the workshop, which is how do you dispatch jobs to jobs that arrive to a set of queues, a set of servers, or a set of computer clusters. And so assume you have an arrival rate R of jobs arriving to a certain dispatcher, and the dispatcher gets to decide which way these jobs are sent for service. So basically, the dispatcher is effectively choosing an element delta in the unit simplex, which basically breaks. So R times delta would be all these rates. They add up to R, and they're all non-negative. And that's what feeds the queues. And then for the queues, I'm sticking to this old model from Stephen, which is the derivative of the queue is input minus output. And let's postpone the discussion of the departure rate, the output. So that's a simple fluid model for the queues. So how would you go about doing this in this fluid formulation? one of the popular strategies to do this is what's called the join the shortest queue policy, which basically says send the job to the shortest queue. And everybody understands this notion. And so basically to let the delta element be just 1, 0, 0, 0, supported in the shortest queue. And this just ties, you can break them arbitrarily. Okay, that would be one way of running this. That actually gives you a dynamics if you do this fluid model with switching along. And that's kind of nasty it gives you a differential inclusion and all sorts of nasty things. I'm going to use the soft min approximation. I guess Srikan already showed this today, so that helps me. So epsilon is a small parameter, and this basically is an approximation to the minimum function. So basically, it would put most of his mass in the shortest queue, but not all of his mass in the shortest queue. Okay, so this would be one way to operate a load balancing scheme when jobs are arising. Okay, but does this apply to our, is this helpful for this problem we were looking at here? Well, the only problem it has is that you need to assume that the scheduler can tell everybody where to go. So it's a mandatory thing. You should go to this station, and people should obey. So it's not obvious that selfish EV drivers will follow this kind of scheme. So that's the third ingredient I need to add into the problem, which is selfish routing. And this also has a very long tradition and history in road transportation networks. So people have looked at, this is a set of roads or freeways. There's people choosing the path. And so all the way back to the mid-20th century, people are looking at what's the right equilibrium flow that comes out of this problem. And so the models typically assume that there's a flow of rate going through each one of these links. There's a latency function or a delay function associated with the flow, and it grows when the node gets congested. Then you can add up the path latencies. This is similar to the internet stuff. And then if you want to, you have a certain exogenous source destination flows, and you need to, they get to choose which path they use, and they're going to choose paths of minimal latency, assume they have the information. So that's actually a game that these guys are playing, and there's a Nash equilibrium of this game, which is traditionally known as the Wardrop equilibrium, which tells you what's the solution you get. And in fact, it was shown early on that there's a convex optimization problem that in this case gets you the solution of this Wardrop equilibrium, even though there's no central planner doing this decision. It's just a spontaneous game, but still you can interpret the equilibrium as if somebody were solving this optimization, adding over links the integral of the latency function. And people have studied what's called the price of anarchy, which is the gap between this allocation and the one you would do if you were a socially benign planner. You would try to keep, this would be a reasonable objective, which is flow times latency is how many people are stuck in each piece of the road. You try to minimize that. Okay, so this is, again, I've gone through 3 pieces of background. Now let me see if I can get you my own formulation for the EV problem and tells you what we've done. So again, we have a bunch of locations in the plane. I is the index for the location. Now there's rates of arrival, so there's requests arriving at these city corners, people who want service. And we have to break up these flows into flows going to the J stations. So Xij will be the flow going from location I to each one of the stations. And I'll tell you in a minute how we will choose the deltas, this split. Then you get to the stations. The stations have a queue, and the queue will be fed, again, a fluid queue, fed by the total rate that comes from every location and some departure rate. And now this is the moment where I want to discuss the departure rate, which we haven't so far. So typically in networking or queuing theory, people think that jobs depart when they get completed, when they're served completely, and this is the most traditional model. We believe that for this application, that's not the best way of thinking about it. You're driving through the city, you're down on charge, you want to get some charge at the parking lot, but it doesn't mean that you want to fill up your battery. You just want some level of charge. And you have some available time for this, sojourn time. You're willing to spend T seconds in this station to get some charge. So we believe more reasonable, of course simplistic as all models are, but model of the procedure is you leave when you have a budget of time, you allocate that budget, and then you leave. And typically that will depend, of course, on each driver to have more or less sojourn time. But let's take parameter t to be the mean of sojourn time. And for now, for a fluid model, you need to take the sort of aggregate quantity. I'll tell you later show you some simulations where you don't assume that. And so the rationale is that you have a time budget, and then you leave. And so with that rationale, then the departure rate from a queue is basically q over t. This would be like a version of Little's law as well. Each vehicle spends t seconds, so vehicles leave in t seconds. Q over t is the departure rate. Okay, so now I have most of the ingredients. Now let's look at delays. As I showed you before in the Monge problem, you have a transport cost. In this case, we're going to assume the transport cost is the transport time going from I to j. So kij, this cost, has units of time. What time? The time it takes you to get to the station. And where do you get it from? You can ask Google Maps, okay, how far am I from each station? We're going to assume that this is exogenous, which means that no matter what decision I make, I won't affect that time. I'm small enough in the system, there's enough background traffic not doing EV charging for now, for a few years, that that is an exogenous quantity. So that's basically an input to a problem. And you can, in practice, you could get that information from a phone app. And then there's the waiting time at the station. And that the model we use for that is the following. If the station in the queue is below its capacity, its number of chargers, then once you get there, you get immediate service. If instead you have extra, there's more people there than you have chargers for, then there's extra q minus j has to be cleared at the departure rate before you can get service. So therefore, this is the function you get, and this is the delay model you end up getting. It's no delay until Cj, and then this hyperbola above. Okay, and so the total delay to receiving surface at station j starting from location I is kij plus mu j. So that's what the selfish driver sees. And that then rationally what they would do is go to the one that has the smallest value, right? Minimize this quantity. Perhaps you need to drive a little bit further to reach our emptier station. So that's a compromise you have to make. Okay, so we're going to put this into our selfish routing model. Only I'm going to, again, do this soft min approximation. This is just for mathematically technical reasons. Oh, by the way, I didn't mention, but this paper is submitted, but it's in the archives if anybody wants to see it. The details are going to be there. Okay, so now I have the overall dynamics. I have these set of queues at the stations. They're draining at rate 1 over t due to this departure model. They're being fed by the input xij from all locations in the plane. These, in turn, are obtained from the exogenous rates Ri multiplied by these deltas, which are the breakup splits of rate. And where are these obtained from? Again, from this sort of soft min operation. With what information? Information of the transport delays, which are exogenous to the system, and the queuing delays, or the waiting times, which in this model take this form. So that's the problem. That's the dynamics we want to study. And we want to, what's the equilibrium resulting from this? Is it stable? This is the kind of control analysis we want to do in this problem. And we're going to rely on optimization, as you probably can guess by now. And I'm going to be using the function, this I'm calling in beta here, which is the integral of this function before. It's a convex increasing function. And it has actually an explicit form if you want it. Okay, so what's the theorem? The theorem says that assuming the exogenous rates and delays are constant, then there's an equilibrium to this solution to this problem, a unique equilibrium, by the way, and it's a solution of this big convex program. And let me parse this a little bit for you. The first term and the first two constraints are exactly the same as in the Monge-Kantorovich old formulation. Basically, is minimize transport costs subject to meeting demand and positivity. There's a difference. The main difference is that the supply constraint is not fixed a priori, and it depends on this variable qj, which has a barrier cost. So it can't go beyond cj with some cost. So that's one difference with the classical optimal transport. And the second difference is this kind of entropy term here. And that's mainly due to this regularization we did to avoid switching. You could put epsilon equals 0, and then you get a cleaner understanding, but then the dynamics will actually have some chattering around the equilibrium. Okay, so, that's the equilibrium. Is there a price of anarchy here? Yes, there is, just like in the road transport case. What would be the natural or the good social cost you would like to minimize? Perhaps the number of people who are in the system and are not yet getting any charge. People who are traveling to a station, or people who are waiting at the station. And that would be a natural cost. So forget about the last entropy term. This function is not the same as this function because of the second term, and therefore there's potentially a gap there. And okay, so you may start to think, and I did think at some point, is this how we added anything to this old road transport literature? Well, it turns out that the main difference is that they use, for model for latency or delay, this primal type model with a barrier function. And that's present in all that literature. And we are using a model which has a fluid queue. So it's basically the dual primal debate. I skipped a comment, which was during 2002, there was an IPAM workshop at UCLA, and we overlapped, I guess, the people here who were doing dual congestion control with Kelly and Vinicom and the people who were doing primal congestion control. And there was this big competition and fights going on as to which was the better model for the internet. It was kind of entertaining at the time. Friendly fight, yeah. So this is kind of the same. I end up in this problem with a dual formulation, and this is just because I'm a religious supporter of Stephen's legacy. Not necessarily. Just I think that part of it is that in this problem, I guess, to get a primal formulation would mean that all the traffic will be subject to this. So you would influence the entire pattern of traffic. Once you go that the congestion is mainly at the stations and the rest is a fixed constant, then this is a more natural model. Okay, so I told you there's an equilibrium, and you can actually prove that it's convergent. Convergent is globally attractive. And to prove this, you actually go entirely by the dual congestion control playbook. You compute a Lagrangian. Of course, it looks very nasty here, but and compute the dual function. And then you show that the dual function is non-decreasing across trajectory, just like Low Lapsley did in their day. And finally, you have to do some control theory to get the global asymptotic stability. Lyapunov, I forgot an A there, LaSalle argument. It's not completely standard. If you're interested, it's in the paper. It took a little bit of an effort. That's why I ended up removing just as much switching as I could from this problem, because it gets very, very technical, and conceptually it doesn't add too much. But it's the only non-smooth you have is this one, which I didn't want to remove. And so I had to do some special argument for that. Yeah. Okay. Okay. So that's the theory. Let me just show you a couple of simulations on how this works in practice. So first, this is a fluid simulation where in this square you have people requesting traffic at an overall rate of 10 EVs per minute. There's 5 stations there which have irregular positions, the same capacity. People will stay for an hour, 60 minutes, and therefore you have that's where you get your sojourn times. And then the transport times, you get them, assume in this case, Euclidean distance divided by some travel speed. So there's no streets, I guess you go directly to the station. It's kind of a cartoon. And the speed is computed so that the maximum transport time is 10 minutes. So most of the time you spend at the station, but still there's some effect of getting there. Okay, so if you start to simulate, and I hope this works, you see initially that the queues are initially empty, and cars start to arrive, and you see the split of traffic according to these Voronoi cells, which basically everybody's going to the closest station. And that makes sense because there's no congestion, so there's only transport in this situation. So then you keep running for a bit until at some point you're going to saturate this station on the right, because it has too much, it's receiving too much input compared to its capacity, and therefore the cells start to deform, and they're no longer Voronoi cells. In fact, you can show that they get hyperbolas as boundaries. and converge to some solution, and it's actually a solution that the theorem tells you it will. Of course, this I'm simulating the fluid model, so this is mainly a very basic validation. Now, you may think there's a lot of unrealistic stuff in here, so the next slide is, let's see if I can get it to work. No, okay, here. Is a stochastic simulation. So what we did is, in this case, to make it more realistic, EVs are arriving at a stochastic process, a Poisson process. They choose a location in the plane uniformly at random, and they discretely assign to the cheapest station. And then instead of a fixed sojourn time, they have a random exponential sojourn time. So it looks a little bit more mixed up, more realistic. But as you see, when you start the simulation, it starts doing what you would expect, the same thing. The breakup is in the Voronoi cells. These are the attachments. And the vehicle's coming in and out. Until, of course, you reach the saturation. And then these cells will start to breathe dynamically with some noise, as you can see. And this is perhaps too noisy for someone's taste, but it will converge in the mean to the fluid solution we have before. So basically, it is a reasonable approximation, even adding all this stochastic stuff in it. Okay, so let me, one more thing, and then I wrap up the talk. The one generalization we did recently was, let's generalize to elastic demand. Again, this goes in the flavor of the internet stuff. Let's say we assume so far the output rate is RIs are fixed, but in practice what will happen is if the delay to service that the system tells you you're going to have to wait all this much to get actually serviced, then some people will not join, will just basically not join the system. So you get a demand curve that as the tau will be the total sum of transport plus waiting, gets big, this will go down. And so can we analyze this system? Well, the dynamics has all the same pieces I had before, but this last piece, instead of R being a constant, R is now this function of delay. And forget about that formula because it's hard to parse in the time we have. But you can interpret this demand curve, as usually in economics, that's something we learned from Kelly, as a inverse marginal utility. And therefore, you can say, okay, this essentially means that you're assigning utility to the vehicle charging in some units of delay. Once you do that, you can write the reasonable optimization problem, which is cost minus utility. Minimize that, or maximize utility minus cost, which is the same thing. Subject to the same constraints we had before, and now this rate is a free variable in the box. If you do that, you can actually extend basically everything I said before, and there's some details because this is not a jointly convex program. Due to this entropy term I had to add to smooth things out. It's not jointly convex, but there's some workarounds which I won't get into. But basically, you can generalize everything I said to this problem. You can show there's a unique equilibrium. The equilibrium optimizes this, and it's globally attractive. Okay, so that's basically it. Let me just wrap up. I'm close to the time. So we've analyzed this dynamics of spatially distributed charging infrastructures, the delays that are considered transport plus queuing, and selfish routing. And so again, this is again a case where convex optimization is used to reverse engineer what essentially the system is actually doing. And as I showed you, there's a lot of use of duality, Lagrangians and all that to prove things. So again, we're following the same old paths. Future things. Well, I gave a first version of this talk, and Kevin was in the audience, and Kevin told me, can you add delay? You add a delay to the internet problem. Why not add it here? And I tried, but these things with routing, delay ends up creating oscillations almost immediately. So this will work provided the delay itself is negligible with respect to the overall sojourn times. Yeah.
Is it single path routing?
Yeah, it's multipath routing. It will oscillate around. So perhaps some of these oscillations we're seeing in the simulation are not just the stochastic noise. There's a little bit of dynamical oscillation as well. So yeah, sorry. Let me go back a second. Then, but of course, I opened the door to the stochastic queuing stuff for the simulation, and I guess I told you some of the stuff we do is queuing theory. So I'm trying to convince Andres to spend some time in this problem, which is it gets the stochastic geometry. We have these cells. So it's probably nice for somebody who knows the stochastics very well, but it's challenging. It's not being done. Of course, I showed you price of anarchy. Every time you see a price of anarchy in this literature, somebody says, okay, what can we do to eliminate it? So we can add some tolls or add some things to incentivize people to do the socially optimal solution, something that could be looked at. And also we've been looking at other applications of the same model. You see, I've showed you load balancing, where there's transport delays and there's queuing delays. In most of the literature of load balancing, everybody looks at the queuing delays, but there's no such thing as transport delays. But it turns out that there are situations where you have something that looks like a transport delay. For example, if you have a situation where you have an edge router, which can, say cloud computing, you have an edge cluster which you can get quick service from, but they perhaps don't have your data, versus going all the way up to the cloud to get service. So those problems, how do you load balance between those things? Well, there's going to be an extra term there, which is the startup time for the edge router, the closest router to get the information to give you a service. So if you write it in the right way, it looks similar. So we're trying to see if we can leverage some of this in that area. And okay, this is it. Thanks. Happy birthday, Stephen. And take any questions. Well, I guess the typical model people would do is just take, I guess, the static optimization type, generalizing the bunch, the optimal transport thing, where you need to couple this. So once you get the equilibrium, go and see if there's, how the equilibrium depends on design parameters, and see if you can, yeah, perhaps. We haven't looked at, but yes. For
locating the station. Just put the position of the stations in.
We did the optimization. It is non-convex. And also the other thing which is kind of cheating is if you assume that you can put a station anywhere in the city, you clearly, I guess Adam will tell us about how hard it is to get people to give you a piece of land for a data center. So typically the way people formulate these things is I have these candidate locations where I can put stuff, and then you get kind of multiplicative thing with a capacity and so the time I looked at it, it didn't look jointly convex. You could do one of these sort of iterative schemes where you place the stations, compute the optimum, and see and iterate. But yeah, I'm not sure if you can so easily convex. The power grid, I'm not sure I did, no.
Yeah. So he got like the best CDC paper prize.
Okay, I'll take a look.
Look at it.
I'll look at it.
Yeah.
Okay.
So a lot of paper.
What results generalize the case when the location of the charging stations is not fixed and dynamic, like mobility on demand services?
What was the last sentence?
Mobility on demand.
Mobility on demand, okay.
Yeah, like assigning taxis to the people who request for some services, and I mean the location of the taxis are dynamics; they are moving around the city. And
okay, so I guess it's related to John's question. If you put as variable the first paper I wrote on this, I was looking at the station location issue. If you make that a variable, then it's not typically easily convex, but there's some workarounds you could do, iterative things. But yes, I wouldn't say you can't do it, but it's not as easy as this. So, yeah, I guess it's perhaps not a complete answer, but.
Last question.
Harvey. You.
Please go ahead.
Okay. I'd like to ask a question about which problems are homologous. In other words, these techniques, which problems are they applicable to? So the two first examples are one, in-network and edge data caches in computing and storage and network system. And the other is data placement at a set of
Yep.
facilities. So those are two current problems.
Well, this one, the one I talked about, as I was saying at the very end, looks similar to this. Given that the data is placed, how do we, choose where to source it from? The data placement, and that's also that's more similar to the problem where you would jointly optimize the stations and the assignment, and perhaps a little bit harder. But yeah, we wrote a grant promising to do all that, but we'll see what we get out of it.
Now's your chance to do it.
Let's thank Philando again, and also happy birthday. Thank you.